All right, so for the very last video, we are going to be looking at the electrochemical series. What is that? You'll know all about it in a minute. And then how it can be used to determine spontaneous redox reactions. So spontaneous redox reactions means, we might actually write that as a question. So question 1, what are spontaneous redox reactions? And they are reactions that occur naturally. So like when we dropped the zinc in the copper, well, we didn't actually do that. We watched a video of it. It occurred naturally. Another example is the rusting of a bike will occur naturally. Some non-spontaneous reactions are like recharging your phone. That's a redox reaction, but you need to actually plug it into the wall, give it electricity to undergo that redox reaction. And also another example would be silver plating and gold plating of your jewelry. That's through a non-spontaneous reaction. So what I want to do is show you again the VCAR chemistry data book. And inside the data book, this is what you can take into the chem exam. Inside the data book, you'll see on page 4, there's the electrochemical series. I would love you to print this out and then annotate it with the way I'm going to annotate it. If you don't have a printer, you can write a few of the reactions and annotate it that way. But first of all, I'm going to start to annotate it. So first of all, you can see that in this direction, you actually have reduction occurring. And in this direction, you actually have oxidation occurring. Oops. Yeah. And you'll see that there are double arrows. And the reason that there are double arrows is because they can occur both ways, depending on what they're reacting with. We know that reduction and oxidation occurs at the same time. So you'll notice here like a set of conditions on the right-hand side. And that's basically saying that these were the set of conditions that were used when this table was created. So really this table is only applicable to 25 degrees Celsius and standard conditions. So you don't have to stress about that right now. All right. So the main thing is a bunch of chemists did a bunch of reactions and they listed the reactions in order. So the reactions are listed in order of most to least likely to occur. So basically that the fluorine being reduced is the most likely reaction to occur. And it makes sense because fluorine is really electronegative, so it's most likely to gain electrons. Whereas if you go to the bottom, you've got your group 1 metals, very unlikely to gain electrons. The important thing is it's actually read both ways. So the reactions are written as most likely to occur as reduction reactions. But if you read it from the other way, at the bottom, you've got the most likely reaction to occur as oxidation. So most likely to occur as oxidation is at the bottom red from right to left, because that's where we've got loss of electrons. So we'll do a little bit of work in this. So the next thing I want you to annotate it with is where your reductants are. So your oxidants are reduced. So all of these are your oxidants. Just make sure you're only circling the one that changes in electronegativity. So here it would be the oxygen. Sometimes it's easier because there's one. So they're all oxidants. I'd like you to actually highlight them all if you've printed it out. And the reductants I'll do in another color are here. It's the oxygen. So reductants. Now, where is the strongest oxidant? Well, that's going to be at the top right. So we're going to write that out. Oh, maybe I have an arrow one that I can use. Cool. So strongest oxidants there, strongest reductants there. So I'm going to write that out. So here is strongest reductants. If you want to color code it better than me, you're welcome to. And on this side, we've got strongest oxidants. Now, going back to our original idea of how can we use this to determine a spontaneous reaction? For a spontaneous reaction to occur, your oxidant needs to be higher up on the series, so stronger than the reductant. So this will be spontaneous, okay? Oxidant and reductant, and this will be the way the reaction occurs. The oxidant will be reduced and the reductant will be oxidized. So you can write that down. You can write oxidant here and reductant here, and then you can write oxidized, and you can write reduced. If the opposite occurs, just have to let my cat out. So if we do put, you know, iodine in with iron 2+, they'll just sit there with each other and they won't react unless we give them electrical energy, but that's saved for year 12. So that's sort of what I wanted to get up to. Now we'll do the one example. Let's head back to our example. Okay, so which of the following examples would a spontaneous redox reaction occur? Explain your answer. This is pretty hard. The reason why is because they're not giving you the like the symbols, what they actually look like on the electrochemical series. So that's the first thing you need to do. So this is an example. All right. Zinc nitrate, we know, is ZnNO3 2. Hopefully you do know that. Zinc is a 2+ charge. And copper metal. And you have to read copper metal as Cu solid. Will they react? Well, if you're going to look for zinc solid, this is what you'll find. Zinc solid is here, copper is here. Both reductants won't react. So it's because we've read it wrong. In zinc nitrate, you're not dealing with zinc solid. You're dealing with zinc 2+. So you really need to look for that and copper metal. So let's try that one more time. I'll go to annotate. All right, so copper metal, excellent, zinc 2+, bye-bye. I like to think of it like a positive gradient, bye-bye, non-spontaneous. So what do you answer for that? Well, you just simply write no, it will not be a spontaneous. So no, and the way you can write it is oxidant is lower on electrochemical series than reductant. Okay, I'll just zoom out a little bit. All right, copper nitrate, again, it will be copper 2+ because it's in a compound, or actually in a solution, and zinc metal. So let's have a look at that one. Not zinc A, zinc solid. Okay. Now we'll go back to this one. So, might just, yep, that's good. Okay, so let's find the two. So copper 2+, excellent. Zinc solid, excellent. We've got negative gradient, so we have a spontaneous reaction. The zinc will be reduced and the copper will be oxidized. So sometimes they'll get you to actually write out the half equations and you just simply copy them from the electrochemical series. So you're writing copper, oh no, that's subscript, 2+ aqueous plus, plus 2 electrons produces copper solid, and it'll be zinc solid for oxidation produces zinc 2+ plus 2 electrons. So you can just get those straight from the electrochemical series, and then you could do the overall. But just to remind you, make sure that these are superscript. And just to remind you, this is reduction and this is oxidation. All right. Now, lead nitrate, lead 2, it tells you Pb2+. Because lead can have multiple oxidation states, being a transition metal. And aluminium nitrate, Al3+. Let's take a look at those two. So lead, Pb2+, and aluminium nitrate. Let's just make sure that lead's not present twice. So lead is there. Okay, so lead is there, and aluminium is here. No, they are both oxidants. They can't react. You need an oxidant and a reductant. So I'm just going to write no, both oxidants. / oxidizing agents. Remember that they need to actually, that word's interchangeable. Solid cobalt and solid tin. I'm already thinking the same explanation, but let's give it a go. So we've got solid cobalt and solid tin. No way, both reductants. So they kind of wanted to give you one of each there. So no, both reductants. Yeah, and if you get 4, reactants chucked in together or more, you're always choosing the strongest oxidant. So for example, if they said cobalt with zinc with aluminium, you'd actually say that, because technically aluminium could react with both, with the cobalt there, it will be reduced in preference. So, because it's the stronger oxidant. So if you're providing the half equations, it would be these two. I think that's the last point that I needed to make.